everyone. My name is Greg Jew with Keysight Technologies. I'll be presenting this next paper, Flexible Testbed for 5G Waveform Generation and Analysis. So today, the standardization process has not yet begun for 5G, but even given that, there is research going on for new types of waveforms, emerging waveforms, at different frequencies and at different bandwidths. And so it's important today in terms of flexibility to be able to generate different types of waveforms at different frequencies and different bandwidths to potentially minimize the risk of maybe choosing the wrong path as candidate waveforms emerge for 5G applications. And so some of the desired test bed attributes include generating and analyzing new waveforms, supporting a wide range of modulation bandwidths from maybe several hundred megahertz to maybe a few gigahertz, supporting a wide range of frequency bands, maybe from RF to microwave to millimeter wave frequencies. And so this is our proposed test bed for 5G waveform generation and analysis. And it consists of software elements as well as hardware elements. The software elements provide flexibility in the types of waveforms that are generated and analyzed. And the hardware elements provide flexibility in terms of the bandwidths and the frequencies of interest. So at the heart of the test bed is this M8190 AWG. And this AWG setup has an embedded controller. This is basically a PC. And on this we have our System View design library installed on the embedded controller, as well as Signal Studio for custom modulation. So this is kind of the hardware component to it, or the software component to it, that is. And the 8190 AWG itself generates I and Q waveforms. These are routed to a PSG vector signal generator with wideband IQ input. So this is what modulates the I and Q waveforms onto a carrier frequency. If we're interested in generating millimeter wave frequencies, we can use millimeter wave up converters and down converters to get up to millimeter wave. We can use MXG signal generators to provide the LOs for the millimeter wave up converters and down converters. For doing the signal analysis, we would pair up a signal analyzer or maybe a wideband high performance oscilloscope for doing wideband signal analysis. So now let's take a look at a couple different case studies to help illustrate some of the flexibility provided by this test bed. And so this first case study is going to be down below 6 gigahertz. And we're going to take a look at one of the candidate 5G waveforms. It's something called FBMC, stands for Filter Bank Multi-Carrier. And so to do this case study, we're going to actually take a look at coexistence between the 5G candidate waveform, FBMC, and a 4G waveform, LTE. And so we are using our System View design library and software to generate the FBMC waveform. It is this path here where we have a bit source. We produce a complex signal, and this gets modulated onto a carrier with an IQ modulator. So this is our FBMC waveform. Down below, we have our LTE waveform, the 4G waveform. Again, we have a complex signal source. It gets modulated onto a carrier using an IQ modulator and then amplified. And then the FBMC and the LTE signal are summed together. They're run into the signal combiner element, which is effectively going to combine and resample the waveforms. The output waveform can be set to a user-defined sample rate. So here we set the user-defined sample rate to be compatible with our arbitrary waveform generator, download the waveform, and then we're going to analyze it with the signal analyzer. So this shows the resulting waveform that got generated, the spectrum. So here we can see the FBMC spectrum. And what we've done effectively is to carve out a notch in the center of that FBMC signal. And in the center of that notch, we have parked the LTE signal. So we can zoom into the LTE signal and we can demodulate it. This shows the demodulation results, showing the constellation, the spectrum. And you'll notice that the EVM, or the error vector magnitude, is about 0.6%. And so this tells us for this particular configuration that there is good coexistence between this 5G candidate waveform and our 4G waveform, our LTE waveform. We don't show it in the slides today because of time limitations, but we have shown this in a webcast and also in a white paper where we can easily change the notch width of this FBMC signal and see where that notch width starts to interfere, where that FBMC signal starts to interfere with the LT signal, and where the EVM starts to degrade as we decrease that notch width. So now let's take a look at a wider band case study, and this is going to be up at microwave frequencies, up at, I believe, 28 gigahertz. And to generate the wideband waveform, we're going to use Signal Studio for custom modulation. There's an easy-to-use graphical user interface. It's kind of parameterized where we can enter in different parameters. We generate the waveform. It produces a file that can then be downloaded to our arbitrary waveform generator. And then in this case, we're interested in a 28 gigahertz signal, so we're going to download I and Q. This gets routed to the rear panel wideband IQ inputs on the SIGGEN to generate our test signal. And so this is what the wideband signal looks like. This is centered at 28 gigahertz with 2 gigahertz of modulation bandwidth. So you can see that the signal is quite wide, spanning the 2 gigahertz of bandwidth. Okay, so now let's take this a step further and let's get up into millimeter wave. So the signal generator that we had used for the 28 gigahertz case study actually has a frequency range of up to 44 gigahertz. So the combination that I just shown previously can generate signals with modulation bandwidths of 2 gigahertz, up to 2 gigahertz, up to frequencies up to 44 gigahertz in frequency. Now for the millimeter wave case study, what we're going to do is we're going to bump down the carrier frequency on this SIGGEN down to an IF frequency, and we're going to run it into a millimeter wave upconverter. So this upconverter is going to upconvert a 5 gigahertz IF frequency up to 60 gigahertz using an LO produced by this SIGGEN for the upconversion process. Now, the output of this upconverter is 60 gigahertz, and we're going to measure this directly with one of our high-performance oscilloscopes. And so it may be difficult to see from where you're sitting, but this is waveguide on the output of this millimeter wave upconverter. And we've got a waveguide to coax transition, and that coax input is then fed into our high-performance scope to do the measurement. So this is at 60 gigahertz. But the scope that we're using is capable of measuring signals directly up to 63 gigahertz. So it has a very high sample rate to be able to digitize the signal and analyze it. And so this shows the measurement result for our 60 gigahertz signal. It's actually 60.48 gigahertz. And we can see the constellation, and we can see the spectrum, and the EVM is low, and we can see that the constellation looks very clean. Now, one thing that we had done for this measurement is you can imagine that if you're going from LT kind of bandwidths, maybe 10, 20 megahertz, and moving up into a gigahertz bandwidth or maybe 2 gigahertz of bandwidth, there can be a lot of amplitude and phase variation across those very wide bandwidths. And so for this case study, what we had done is we turn on the adaptive equalizer, which would normally be shown here. And when that adaptive equalizer is running, what it's doing is effectively minimizing the amplitude and the phase variation across this 2 gigahertz of bandwidth. And so this is shown kind of graphically here where we have the adaptive equalizer running. Here's the real and imaginary response. So this is a complex response, amplitude and phase. After the adaptive equalization process is finished. And then we use our seamless integration between our design software and our test equipment to read this in and apply it to the waveform. So we're effectively pre-correcting for the amplitude and phase variations over this wide bandwidth to pre-correct the waveform. And so this measurement result is after we have pre-corrected that waveform. So you can see that the adaptive equalizer is disabled or turned off for this case. And we're getting this kind of constellation EVM result because we have pre-corrected the waveform. So in summary, I've talked a little bit about kind of a flexible testbed approach for 5G waveform generation and analysis. And again, we think this is key because today 5G is not yet defined. The standardization process hasn't started. So flexibility is key in being able to quickly adapt and modify waveforms, different frequencies, different bandwidths as 5G evolves. The flexibility in terms of the waveform types, both generation and analysis, are provided by software. So that provides flexibility in the types of waveforms that we generate and analyze. The flexibility in terms of the bandwidth and the frequencies of interest are determined by the hardware selection. We took a look at a couple different case studies. One was down below 6 gigahertz, and this was our coexistence case study between this candidate 5G waveform, FBMC, and LTE, our 4G waveform. And then we looked at some wideband waveform signal generation and analysis case studies at 28 gigahertz and 60 gigahertz. And so if you get a chance to come by the booth, we're showing a demo at 72 gigahertz with 2 gigahertz of modulation bandwidth, so it's kind of an extension of what I'd shown here. There is also a white paper available for you to download to get more information on this. And there's also a webcast that we'd recently done, and the archive is available for you to view. And so with that, I'd like to thank you for your time today. Thank you.